So my name is Stoyan Rachev. I work as a software engineer at Uber, and I would like to talk about dependency injection, and specifically about the Uber's FX framework. I guess you should be at least somewhat familiar with dependency injection. So can you raise your hand if you have heard about it? Okay, so that's not surprising because dependency injection is kind of mainstream in many other languages, and especially in the Java ecosystem with Spring and with CDI. But we will not be talking about all these other languages today. Dependency injection is relatively, I would not say it's not native to Go or that it's not mainstream, but frameworks that actually facilitate composing applications based on dependency injections are rather rare. And FX is, I would say, one of the first really interesting attempts to create such a framework. But to understand, I will not be comparing that to what we have in the Java ecosystem space, but instead start from the problem that we're trying to solve as Go developers. Okay, so what exactly is dependency injection? We start with what dependency injection is not. So on the slide, you see some examples. The first one is instantiating dependencies yourself. And the second one is depending on global state. There is a global variable called logger, and your code in the new handler constructor will actually use the logger to output some logs. Both approaches are not really good. The first one is obviously really not good because if you instantiate everything that you need, you can't really share those dependencies. And that's essential in many cases. Your code is definitely not testable and not composable. The second one allows for sharing. However, it has really many inherent problems. And nevertheless, this is a widely used technique, even in the standard library of Go, as we will see a bit later. So what are the actual issues with that? There are some quotes from articles written by thought leaders in the Go space, recent articles, both are from 2017, in which we see that there's actually kind of a movement in the Go ecosystem to go into, to somehow avoid using global state. Why is this the case? So basically, the idea is that global state hides things. You have dependencies that are not explicit, meaning you are, when looking at the signature of the functions, it's not possible to really understand how this function interacts with other parts of your program. And basically, state is being smuggled between different unrelated parts via global variables, which increases the coupling between your modules. Very importantly, it also makes your functions very hard to test. So it's completely not trivial to replace global variables with something that is actually testable. So both Peter and Dave are strongly in the opinion that this should be avoided. If we avoid that, so what we need to do? So what we need to do is dependency injection, basically. In the Go language, that is actually a very simple language. Dependency injection takes the form of simply passing a parameter to a function. So instead of either instantiating our logger or depending on a global variable, we will be accepting it as a parameter. So it's as simple as that. And we have two options. We can inject a concrete type. So basically, in this case, a pointer to logger, which is a type from the standard library, concrete type, or we can inject an interface. And if an interface does not exist in the standard library, we can always create one ourselves. You know that with Go, this is very easy. Why is this good? Now, we are elevating our dependencies to parameters, making our functions, making all of our dependencies explicit, making our functions easier to understand, easier to reason about, easier to maintain, and much easier to test. And The benefit is especially visible if we rely on interfaces instead of concrete types, because with an interface, we can very easily supply a different implementation. It can be a mock. It can be a completely different type that still adheres to the same interface. The accepting code doesn't even need to know that as far as the interface is fulfilled. So this is what we want to do. I would like to demonstrate now how we can actually benefit from this technique by looking at a very simple example. So let's see this example here. I'm starting from a state where everything is in main to make it very clear. There's actually a very simple thing. This is a very simple web server that registers a handler on the 8080 port, outputs hello world to the response, and logs a message to the logger, in this case to the standard out, with the handler code. So you see we have 4 parts: creating the actual logger, creating our handlers, registering the handlers, and starting the server. From the perspective of a service developer, there is one interesting part in this whole main function, and this is the actual content of handler func. So these 2 lines, this is our business logic. Everything else is really infrastructure, creating loggers, starting servers. We don't really want to care about these things. Code is really that simple. We will typically avoid putting everything in main. We will modularize. We will create functions and packages in order to make our code more modular and more maintainable. Before we go further, I would just like to show you that this actually works. So let's start our server. And let's curl, oops. Okay, so it works. And it does what's expected. So let's see how we can modularize this. A very first attempt will simply take the 4 sections from the previous slide and encapsulate this code as functions. So we'll have a new logger constructor to create the logger. We'll have a new handler that will accept the logger, dependency injection, to create the handler. And we will have 2 more calls to actually register the handlers and start the server. And let's look at the new logger implementation in a bit more detail. We've already taken the step to encapsulate the actual behavior of the logger as an interface. So new logger does not really create an implementation. It only, so it creates an implementation, but it returns an interface type. Our new handler constructor depends on an interface type, not on a concrete type. So that's the very first initial step. And the second very logical step is, now that we have different functions, those functions have really different purposes, and they have different concerns, and therefore they naturally belong to different packages. So we would put the logger constructor in a package called, let's call it logger. We will put all the logic with registering servers and starting servers and so on in a server package. And we will have a separate handlers package, which will actually contain our handlers. It's a single handler in this case, which is really the business logic that we care about. Everything else is library code. Typically, we will be depending on many such packages in a typical program. Some of them will be our packages, others will be library packages. We'll have a number of such dependencies. And what we will have in main is, of course, not just 4 lines of code. We will have a much bigger number of lines in which we create certain dependencies and inject them in different places. This is called manually building the object dependency graph, or also known as manual wiring. There is no difference in any difference to the actual implementation of our program. The only difference is we put different things. We put the different constructors into different packages. This is where you basically want to be. This is where you want to be if you are not using a framework such as FX. you are taking full advantage of dependency injection. All of your handlers are testable. Isolate and modularize your packages in the best possible way. However, you still have to deal with this manual wiring stuff. One may argue that this is still better than using global variables, than using any other approach, and that's true. However, this is still not ideal. One of the reasons why we created at Uber a special framework for dependency injection is that dealing with manual wiring is actually costly. And this is, I'll try to explain why is it costly. So in a big enterprise, you typically have two types of developers broadly. You have developers that are mainly focused on libraries, and you have engineers that are mainly focused on services. So you want to focus on pieces of code that are frequently used by every service, and you want them to be able to evolve independently of the services, and you want the things that happen there to be adopted by all of the services. Manual wiring makes all of this difficult because from the library owner's perspective, wiring things manually requires code in every service. And it's not enough to just put this code there and forget about it. Since libraries will evolve, service owners will have to maintain this manual wiring. That may amount to hundreds of lines in your main Go. What will happen is that first of all, this is complex. You need to know how to manually wire each and every of your dependencies, which will inevitably cause some confusion. Second, it will change over time. So you will need to maintain this code over time. And different service owners will do different things. Some will adopt every change rather quickly. Others will fall behind. Yet others will be somewhere in the middle. And services will diverge gradually from this perspective. What could library owners do to avoid this cost for the service owners? Not surprisingly, one of the things that global state actually solves this problem at the expense of everything else that we talked before. And if I go back to the code, if you look carefully, there's global state here. Can you spot it? Do you know what this parameter is? Probably you don't, so I will explain. So to actually initialize a server, you need something called a servmax. This is a multiplexer that will route paths to handlers. And there is always in the HTTP package of Go, there's always a servmax. However, very often we have just very few handlers, and it's completely okay that they use the same servmax with some default initialization. So this is why the library creators have created the default servmax, which is what? A global variable, of course, in the HTTP package. So when you are calling the handle function, it's actually using the default servmax. And when you are calling listen and serve with new parameter, it will actually use the initialized default servmax. So this is hidden global state. This is the place where we don't want to be because our code relies on magic and we don't know what's actually happening. But you see, even the standard Go library relies on such mechanisms, exactly to save us from the necessity to each and every time initialize the servmax and inject it somewhere, which will be boilerplate that we definitely don't care about, but we will have to write and maintain. So this is why, this is in few words, why manual wiring has a cost, and solving it is not really simple. Like resorting to global state is not really an option. Not sharing concepts between different libraries is another way to go. It's also not an option. It results in increased complexity and duplication of concepts among libraries. So there is no easy way around this. So this is why we created a special framework for that. It's called UberFX. It's actually called FX, not UberFX, but it comes from Uber. And what it is, it's a modular service framework that makes it easy to create services and composable modules. And it captures all the benefits of dependency injection that we talked about, but it also eliminates the cost of manual wiring. There is completely no manual wiring if you're using FX. You get all the benefits from not having manual wiring. This means library owners can evolve their offerings gradually. Service owners can focus on their business logic. From the company perspective, all services will be consistent, and it will be very easy to roll out new offerings and sunset old offerings without causing huge amounts of friction. And so how then does it work? So let's look now at our main using FX. So it obviously looks completely different from what we saw before. And I'll try to explain what actually happens here. We are creating an object that is our application using the FX new constructor. And using the so-called option design pattern, we are passing certain things to that. So we are passing two modules called server FX and logger FX. And we are passing, via the FX provide option, we are passing the constructor of our handler. There can be multiple handlers. If we had more than one handler, so we would simply list them. And then we say just up run, and all the magic happens. Independently of what happens inside your library, inside the libraries, your main will always look like this. Or it will evolve only as far as you have your own constructors. You will increase the list in the provide option, but everything else will remain the same. Now, let's look at it from the library perspective, how actually it looks like. So it's exactly the same logger package that we saw before. It's just renamed to logger FX, and we are providing our constructor to the FX framework using the FX options function call and using the same FX provide option. So we are providing our logger constructor to the FX framework, in essence, getting the framework to know about our type, and it will be instantiated and injected whenever it is actually required. Now, I know this is rather hard to grasp, so I will show now the complete code. So this is our main, but we also have few modules. This is our logger FX module. As I said, it's exactly the same module with the actual module initialization at the top. But let's look at the server module. That's more interesting, right? So the server module has the functions register handlers, which is, by the way, exactly the same as before. And also the function init server, which is very similar, but actually with one additional piece of coding here. So in the init server, we will be registering a hook to the FX lifecycle. And the hook has two callbacks, on start and on stop. On start will be called when our application is actually started. On stop will be called when our application is actually stopped. And in the on start callback, we will start our server. In the on stop callback, we will do whatever cleanup is needed. So, and then what we do with these two functions, we register them using the invoke option. In the invoke option will be used by the FX framework to call things just before the application lifecycle is started. So you will see that shortly in the example. The handlers package is exactly the same as before. There are no changes here. So the changes are in the library packages. They are providing the modules we are composing, but our package that contains our business logic hasn't not changed by the fact that we are using FX. The only thing that changed on our side is main, and main changed once and will remain as this, as you see it, for quite some time. So now let's see if this works. I'm running our server. And now we can see, because of this helpful output from FX, what actually happens here. So what happens is that, first of all, three different types are being provided to the framework. So for the first one is our logger. The second one is the logger from the logger FX library. The second one is our handler from our application. The third one is the FX lifecycle type. It's something standard from the FX framework. By providing these types, the FX framework knows about them. Then the two calls that are registered to be as invoke are being invoked. So first register handlers is being invoked, and then init server is being invoked. Since those will actually accept dependencies, FX will instantiate the dependencies that are needed. It inject them whenever these are called. Application is started, and the onStart hook that's also in init server is called. So now our server is running. We curl localhost, it works, obviously. And now if I go and stop it, we see that interrupt is intercepted by the framework. The onStop handler, which is in our init server function, is called. Then let's look at the next logical step. Now, this is all good. However, in a typical enterprise, we will have a large number of such libraries. We have a few dozen in Uber, actually. And we would not like to list them all in this in our mains. So this is another form of maintenance, because if new libraries are thrown at us, we'll have to add them. If some of them are deprecated, we'll have to remove them. We don't want to do this. What we want to do is this. So we have only one or very, very small number of actual modules that contain all the others. We only use that in our main, right? And that's it. So the main never changes. Besides the list of constructors in provide, which is something that we control, nothing else changes in main. And this is possible because it's actually possible to compose modules based on other modules in FX. And what makes this very easy is this syntax here. So we are passing to FX options, now not specifically new constructors, but existing modules. And we have infinite nesting of this, infinite composability of modules that can contain other modules, that can contain other modules, and so on. So in truth, in Uber, we have just one module that is used by all services. It's called UberFX. And we have another one that is used by most services for making RPC calls. It's called ERPCFX, and that's it. Say I just want to give you some takeaways. So first of all, you should use dependency injection independent of whether you use FX or not, because this is the best place to be, probably in every programming language, specifically in Go as well, because it helps you write code that is easier to understand, maintain, test, reason about, all of these things. And second, if you are in the situation in which we are, so if your enterprise is sufficiently large, if you are depending on large number of libraries written by others, and you want to make this evolution of both library code and service code as smooth as possible, you should really take a look at this FX framework. It's open source. It removes boilerplate, it ensures consistency, and it introduces composability. And it's actually, from my perspective, has proven, at least from what I've seen internally at Uber, its value. I would have to say, okay, so this is it. And